Introduction to Dynamic Programming. Hello, everyone. We are going to discuss an essential concept in algorithm design, which is dynamic programming. Dynamic programming, or is called DP, is a method used to solve complex problems by breaking them down into simpler subproblems and solving each subproblem only once uh, and storing their solutions. This technique is particularly powerful for optimization problems, such as uh, finding the shortest path in a graph, resource allocation problems, and more. Um, So we're going to focus on the key concepts, which are overlapping subproblems and optimal substructures. Basic concepts and terminology. So uh, let's start with the basics. Uh, we're going to define some key concepts and terminology in dynamic programming. When we are talking about overlapping subproblems, we are referring to subproblems that recur multiple times in the problem-solving process. An optimal substructure means that the optimal solution of a problem can be constructed from the optimal solutions of its subproblems. And memoization is an optimization technique where we store the results of expensive function calls and reuse them when the same input occur again. On the other hand, tabulation involves solving the problem in a bottom-up manner by filling up a table. Steps to solve a problem using dynamic programming. So we're going to go through the steps to solve a problem using dynamic programming. We first want to identify if the problem can be solved using dynamic programming by looking for overlapping subproblems and optimal substructure. Second, you want to define the state. What we mean by that is states are the variables that represent the subproblems. Third, you want to formulate the state transition relation. So you want to determine how to express the solution of a problem in terms of the solutions of its subproblems. Fourth, you want to initialize the base cases. So you want to identify and initialize the simplest subproblems. And last, you want to compute the final solution using the state transition relation to iteratively solve all subproblems and construct the solution to the original problem. Common dynamic programming problems and examples. So we're going to look at some common problems that can be solved using dynamic programming and their examples. We're going to start with the Fibonacci sequence problem, where we need to compute the nth Fibonacci number. And the next one is the knapsack problem, where we aim to maximize the total value in a knapsack given its weight capacity. Finally, we have the longest common sequence problem, which involves finding the longest sequence present in both sequences. example 1, Fibonacci sequence. So here is our first example. So the problem is to compute the nth Fibonacci number. So using dynamic programming, we can solve this with a bottom-up tabulation approach. In this approach, what we can do is we can create a table to store the Fibonacci numbers up to the nth number and iteratively compute each value based on the two preceding values. And this approach ensures that we only compute each Fibonacci number once. So therefore, we are leading to an efficient solution. And if we look at this implementation, we can see that we have dp, and then dp of index 1 is 1, and then we will use for loop to just add both numbers to find the value in the next index. Example 2, knapsack problem. So given weights and values of n items, what we want to do is put these items in a knapsack of capacity W to get the maximum total value. So using dynamic programming, you can solve this problem by creating a table where each entry dp index I w represent the maximum value that can be achieved with the first I items and a knapsack capacity of W. So similar to Fibonacci sequence example that we saw, we're gonna use a bottom-up tabulation approach. That means we will iteratively fill this table using the state transition relation. So we're ensuring that we consider whether to include each item in the knapsack or not. Example 3, longest common sequence problem. So the task is to find the length of the longest subsequence present in both given sequences. So using dynamic programming, we can also use a bottom-up tabulation approach. So we'll construct a table where each entry dpij represents the length of the longest common subsequence of the first I characters of one sequence and the first j characters of the other. So by filling this table iteratively, you can find the length of the longest common sequence efficiently. Top-down versus bottom-up approaches. So there are two main approaches to implementing dynamic programming, top-down and bottom-up. So the top-down approach, also known as memoization, it starts with the original problem and breaks it down into sub-problems, solving and storing the results to avoid any redundant work. And the bottom-up approach, as we saw from previous example, It's also known as tabulation. You start with the simplest subproblems and iteratively solve them to build up solution to larger subproblem. So an example of the top-down approach can be seen in the Fibonacci sequence here. So we are storing the results of the subproblems in a memo dictionary to avoid recomputing them. Practice problems, if it's your first time running into dynamic programming, it can be confusing. So in order to solidify your understanding, here are some practice problems you can try. The first is the coin change problem, where you need to find the minimum number of coins required to make a given sum using an array of coins. And the second is the edit distance problem, where you find the minimum number of operations required to convert one string into another. And lastly, we have the house robber problem, where you need to determine the maximum amount of money you can rob tonight without alerting the police, given an array of non-negative integers representing the amount of money in each house. These are well-known dynamic programming problems, so I encourage you to search and look these problems up to have a better understanding. Conclusion. So in summary, dynamic programming is a crucial technique in algorithm design that optimizes by storing solutions to subproblems and reusing them. It is particularly useful for problems with overlapping subproblems and optimal substructure. So in this lecture, we looked at the steps to solve dynamic programming problems, common examples, and the two main approaches, which are top-down and bottom-up. That's everything we have for this lecture. Thank you, everyone, for listening.